Hello, my people. I hope we're doing well today. This is 5.5, and in the textbook that I'm using, this is what is known as additional trigonometric identities, and that includes not only these double angle identities, but all of these as well. And like I said before, this grouping over here, I'm not going to require you to memorize. But these two sessions I will. This is 5.4 and this is part of 5.5. The great thing is that they are related. And in this first video, I'm going to derive all the double angle identities for you and do some evaluation problems. In the second video, I'm going to do some verification problems, and it's my intention to put the equations in the third video. We'll see how that shakes out. All right. Now, like I said before, you have sine of 2x, and that is, of course, related to the sum identity. And the sum identity is, sine x cosine y plus cosine x sine y. Now, remember that sine of 2x is simply a shorthand way of saying sine of x plus x. So if I actually use the sum identity in the same way, just replace the y's here and here with x's again, I wind up with two terms that are identical. Because multiplication is commutative, this over here is the same thing as that. And so sine of 2x is 2 sine x cosine x. Yay! Okay. Now, like sine, cosine of 2x is related to its sum identity. And you get cosine x cosine y minus sine x sine y. And what I get is cosine of 2x is equal to cosine of x plus x. And that's cosine of x minus sine x sine of x. And that, of course, is going to be cosine squared x minus sine squared x. Yay! Okay. Now, but from what you saw on that cute little identity page that I gave you, there are 3 different ones for cosine of 2x. So let's go ahead and take a look at the 2 equivalent forms of that. And we'll go ahead and draw a cute little dividing line down here. Now we're going to start on both of these with cosine squared x minus sine squared x, because that was the first form of cosine 2x that we encountered. But I also know my Pythagorean identities. And Pythagorean identities are wonderful for changing cosine into 1 minus sine, and for changing sine into 1 minus cosine. Now this one over here, we simply have to slip off the parentheses since they're not really doing anything besides grouping terms, and you get 1 minus 2 sine squared x. Over here we have to be careful to distribute the negative, and that's going to be it's going to give us a positive cosine squared, which couples with this one. And so they look the same. They're just sort of flipped around, right, because of the distributing of this negative. Now, when we get to tangent of 2x, we can do it one of 2 ways. We can actually deal with it as tangent of 2x is equal to sine of 2x over cosine of 2x, or we can deal with it as tangent of x plus x. Now remember, and I forgot to do this up here, but remember that tangent of x plus y is tangent x plus tangent y over 1 minus tan x tan y. And we can use that to make it tan x plus tan x over 1 minus tan x times tan x, and we wind up getting 2 tangent x over 1 minus tangent squared of x. Ta-da! And that is how we derive all 5 of these. And they wind up being really, really helpful, oftentimes more helpful than the sum and difference identities. But let's go ahead and use these to do some evaluation before we move on to verification and solving of equations. Now, I have tangent theta is equal to 5/12. Now this designation right here tells me, okay, because tangent can be positive in either the first or the third quadrant. This tells me that it's quadrant 3, okay? Between pi and 3 pi over 2. So what I'm going to do is I'm going to go ahead and draw it, and I'm going to try and draw it at least a little bit to scale, because I'm going to do a little bit of reasoning out of where it lies in the Cartesian plane, okay? So let's say that that's 5, and that's 10, and that's 5, and that's 10, and that's 15. So the opposite is going to be 5. The adjacent is going to be, and let's ish 12 to be right about there. So this right here should be the trajectory of the terminal side of an angle in the third quadrant that has that ratio of -5 to -12, okay? Now, notice, I need you to notice that because the opposite is smaller than the adjacent, this is closer to the x-axis than it is to the y-axis. Now, the reason why I'm saying that to you is because it's going to be, well, not crucial, but helpful when I start trying to figure out what 2 theta is. Because if this is theta, I was told that theta is between pi and 3 pi over 2. But if I'm trying to discern what quadrant 2 theta is in, and I start off with this 3 pi over 2, if I double all of these, then I know that 2 theta is between 2 pi and 3 pi, but it can be in either the first or the second quadrant. But if I know from observation and drawing it out that theta is between pi and 5 pi over 4, okay, then when I double it, I get a much better idea. 5 pi over 2, I get a much better idea. And this tells me that 2 theta is going to be in quadrant 1. Okay, well, that's all well and good. Let's go ahead and figure out cosine of 2 theta. Now, remember that if this is 5, this is 12, then the hypotenuse is 13, and we can actually figure out anything that we need in terms of cosine 2 theta. Now, if we have cosine of 2 theta, we can use any one of 3 identities. Now, it doesn't really matter to me which one. Let's go ahead and use 2 cosine squared theta minus 1. Now, cosine squared theta for this angle measurement right here is going to be adjacent over hypotenuse. So it's going to be, that means that cosine theta, if tangent theta is 5/12 and it's in the third quadrant, the corresponding cosine theta is -12 over 13. It's, not fun quantities to deal with, but doable, right? And so that winds up being 144 over 169 when it's squared, right? And we're going to get 288 over 169 minus 1. Well, 288 minus 169. Okay, well, let's ignore the 100 and the 200 for a second. 88 minus 69 is 19. So what should happen when you basically change that to 169 over 169 is you should get 119 over 169, and it's in the first quadrant, so cosine should indeed still be positive at that point, okay? Now, that is evaluating. And, you're just going to be using kind of just observations from this picture, just as sort of guardrails. It's almost like putting rails in the gutters when you're just starting to bowl, right? Just kind of helps you kind of get the feel of it before we start doing stuff that winds up being really, really nasty. Now, let's go ahead and do one more evaluation problem before we move on to some verification in video 2. Now, this is sine theta is equal to 2 root 2 over 3, and it says theta is between pi over 2 and pi. That means it's in quadrant 2. Well, let's go ahead and draw that in quadrant 2. Now, that is actually winds up being sine theta, if you sort of unsimplify it, that's root 8 over root 9. Okay? Now, if root 8 is the opposite side and root 9 is the hypotenuse, those are really close. That means that what you have for the adjacent side is just -1. Okay? Because 1 squared plus root 8 squared equals root 9 squared, because 1 plus 8 is 9. And so if you recognize the fact that 2 root 2 is close to 3, it's actually 2.828. So 1, 2, 3, and what you're going to get is you're going to get something like this. So that right there is theta. This right there, let's go ahead and drop that altitude. This is going to be 2 root 2, that's -1, and this is 3. Okay. Now, what we need in order to find tangent of 2 theta is we need, well, we can either find tangent of theta. Yeah, let's go ahead and do that. Tangent of theta, so tangent of theta in this particular one is going to be -2 root 2, right? Opposite over adjacent for your reference angle theta prime. Now, notice that this is much closer to the y-axis than it is to the x-axis. That means that theta is between pi over 2 and 3 pi over 4, which is going to make it a little bit nicer when I double, and it tells me that 2 theta is going to wind up being in quadrant 3. Alrighty, I have tangent, I have the quadrant that it's going to wind up in, and I know that tangent of 2 theta is going to be 2 tangent theta over 1 minus tangent squared theta. Okay, that's, and if you want to actually, call that -√8, since you're going to be squaring it and everything anyway, then by all means, go ahead, or at least know that it's both of those, right? So 2 tangent of theta is 2 times -2 root 2, okay? And then it's going to be 1 minus, and that is going to be, when you square root 8 or -√8, the negative goes away and the root goes away and you get 8, okay? So you're going to wind up with -4 root 2 over -7, or 4 root 2 over 7, okay? And it turns out positive, confirming the fact that it winds up being in the 3rd quadrant, okay? And so that's helpful. All of this is really just a matter of, like I said, it's the rails in the gutter when you're going bowling for the first time. It's to sort of guard you from making egregious mistakes and confirming the fact that you're on the right track when you wind up with a positive answer for tangent to theta. Now, that brings us to the end of our little foray into deriving those double angle identities and using them to evaluate. In the next video, which is likely to be a little bit longer than this one, I will be dealing with some simplification and verification problems, so changing the form. And then in the final video, we will look at some equations and solving them, since we didn't get all the way to that in class today. If If you have any questions, please do shoot me an email or a message on Teams. Bye.